Continuing here with question number 6, notice that we have a difference of squares. It is a fourth power difference of squares, but it is still a difference of squares on the left-hand side. And on the right-hand side, we also have another difference of squares. Now, hopefully you will recognize that the left-hand side, one of its two factors is the right-hand side. So that's very suggestive that we go ahead and factor. So what we would see then is that we are factoring the left-hand side difference of squares, a square of a square, into a minus b, a plus b. Except that in this case, the a minus b is actually an a squared minus b squared. Why? Because it was going to be an a squared squared if the original was an a to the fourth power. Alright, so now continuing here, we have the sine squared theta minus cosine squared theta, which we keep. But then we are going to be using the sine squared theta plus cosine squared theta gets replaced with 1. The sine squared theta minus cosine squared theta is going to stay the same, and now the right-hand side is equal to the left-hand side. Alright, so for question 7, this is one that's very similar to what we did in class for the lecture. You're going to want to go ahead and draw a vertical line underneath to remind yourself that this is not a proportion, so we don't just cross multiply. Okay, so what we want to do then is have a vertical line, and then we're going to recognize that we have a conjugate pair here, and even though we can't cross multiply, this is at least suggestive of where we want to head. If we know we want to have a 1 plus cosine alpha in the denominator on the right hand side, then on the left hand side we're going to want to go ahead and multiply by the very thing that we want to have in the denominator. So we want a 1 plus cosine alpha over 1 plus cosine alpha. So multiply by what you want and then see if you can make it work. So now obviously on the bottom I now have a sine alpha times a 1 plus cosine alpha, so that's more than what I want, but in the numerator I can see that I'm going to get a difference of squares that is going to end up becoming 1 minus cosine squared, which then can be replaced by sine squared, so that's very promising. So now for my numerator, I will replace the 1 minus cosine squared with a sine squared. And then now you can see that one of the sine alphas from the numerator is going to cancel with one of the sine alphas in the denominator. So here I'm going to show this cancellation using check marks. And then what is the next line? The next line is precisely what I have here over on the right hand side. So I would want to copy that right here at the bottom. And that then is your finished product for that one. Alright, now moving on to question 8. We have two fractions that need to be combined. They do not have the same denominator, so we need to multiply each by whatever the other denominator is to get a common denominator, and then hopefully that's going to lead us to something we can simplify into 2 secant x tan x. Alright, so first we're going to go ahead and draw that vertical line as before. And now we would need to rewrite these fractions. And so I wrote the line completely again and then multiplied each fraction by what I need to multiply it by in order to get that common denominator of 1 plus sine x, 1 minus sine x. And so then that leaves us with one big fraction. And then using the distributive property in that big fraction to distribute the negative to both the 1 and the negative sine x, then we end up with 1 minus 1 and 1 plus, and then sine x plus 2 sine x. So this is a, 1 plus wrote this wrong. 1 second. The 1 minus 1 will cancel in the next step, and then the sine x plus sine x will combine in the next step, and the denominator here is cosine x. So I'm going to continue over here on the right-hand side as though I were continuing on the left, but I'm running out of space. So what I end up with then is a 2 sine x over cosine squared Right, so what I would ask you to do, since I have not the space here on the screen to otherwise do it, is to view that these steps are all on the left-hand side. So imagine that these steps, this is step number 1, or step number 1, step number 2, step number 3, and then as I come here to the right-hand side, these are continued steps actually from the left-hand side. Imagine that I'm just going back up this way now. So this is step number 4 on the left-hand side. Step number 5 still on the left-hand side. And then for step number 6, still on the left-hand side, then I want to combine them. Now, when can you go on both sides? You can go on both sides in any situation, but what you want to do is have your last line on each one be equal to the same. So wherever you stop on the left or wherever you stop on the right, you just want to make sure your left and your right side have the same last step. For step number 6, then, I am going to now rewrite this as 2 secant x tangent x. This was my 6th step then on the left-hand side. You'll note that in some cases I'm using the parentheses, in some cases I'm not. The parentheses around the x is really unnecessary if there's only a single symbol, such as an x. If there's ever a negative x or a 2x or something else to complicate a single symbol into something more than one symbol, then you would want to have the parentheses. But in a case like this problem where x is the only symbol after the trig function, the parentheses are optional. Okay, so we'll pick up with number 9 in the next video.